Welcome to the second part of my video about how a distant but mysterious object shook our entire solar system and our scientists, and therefore us, with its 142 milliards. In this part of the video, we will take a detailed look at what this might signal to us. Make yourself comfortable. Thank me with a like, and I'll get started. Impact on Earth. The planet shivers briefly. While the decoders argued about frames, the planet answered with a small involuntary twitch. During one transmission window, magnetometer stations at mid-latitudes logged a subtle deflection, barely above background time to the start of the 142 session. Space weather indices were quiet. The sun wasn't flaring. Yet the trace bent, held, and relaxed in step with the frames like a heartbeat, reaching through the ionosphere. Let me explain why that matters. When the magnetosphere moves, you ask the sun first. Solar wind speed, density, interplanetary magnetic field orientation, none justified the blip. The timing was too neat. 30 seconds after the first prime-framed header, ground magnetometers recorded a bump. 30 seconds after the train ended, the trace eased back. It's small, but the alignment raises eyebrows in a lab that's allergic to coincidence. Unknown to them, a high-frequency radio network monitoring global propagation noted short-lived fading on transpolar paths. Operators blamed nighttime quirks. But when logs were re-examined with Atlas's session times overlaid, the fades clustered inside the windows. Radar facilities running passive modes saw momentary noise floor lifts around 142, localized in time, but not obviously localized in sky direction, like the ionosphere briefly rang at the hydrogen line. Here is what is strange. You don't inject power into the ionosphere at 142 and expect a show. The hydrogen line isn't a standard ionospheric resonance. Yet communications receivers reported microbursts of static precisely when the sidebands brightened. The anomalies were weak, local, and inconsistent across stations, just enough to be dismissed until you factor the schedule. When the clock ran, Earth fidgeted. We test the solar control hypothesis anyway. KP and DST indices stayed low. The auroral electrojet remained quiet. GOES and DS COVAR showed nothing that could stamp a precise multi-minute cadence. If you had engineered a planetary-scale test signal, you'd choose a frequency that passes through our noise without frying anything. The hydrogen band is protected, quiet, and symbolically loaded. It is also a poor hammer for brute force coupling. That paradox bothered everyone. So a different mechanism enters the conversation. Resonance by precision, not power. Think push a cruise ship with a leaf blower, but do it rhythmically at the ship's natural sway. The signal's extraordinarily stable, timing-low jitter, atomic clock discipline, could entrain tiny, phase-coherent responses in layers that already carry oscillations, like the ionosphere's E and F regions. The energy remains minimal. The synchronization does the work. Parallel action, VLF and ALF monitoring stations check for Schumann resonance shifts. Earth's global electromagnetic hum. Most see nothing. A few report fractional nanotesla changes coincident with 2 frames. The signal-to-noise ratio is abysmal, but the timing hooks analysts. Even skeptics admit the coincidence is uncomfortable, then insist on more runs. That is the right instinct. Ground truth came from an unexpected source, a national standards lab that keeps an ensemble of atomic clocks. Their time transfer logs showed picosecond level jitter spikes in a fiber link exactly once during a prime header. It's almost certainly local noise. Yet after the lab deratated by sidereal time humoring, the hypothesis, the spike aligned with a similar anomaly at a second site during a different session. 2 points don't make causality, they make you widen the net. Now, communications. Amateur radio operators noticed short-lived narrow notches near 142 when scanning the band with spectrum scopes. Many were false alarms. A handful matched session windows to the minute. The notches weren't RFI spikes. They looked like receiver front ends briefly desensing saturation-like behavior, though the incoming power should have been far too low. That hint dovetails with a possibility few wanted to say out loud. High gain, pencil-thin emissions sweeping Earth can produce locally intense fields without global power. If the beam touched a receiver front end directly, even for milliseconds, a modern low-noise amplifier could burp. Let me clarify the stakes. We're not just listening. We might be inside the experiment. If an external, disciplined source is probing the hydrogen line with a beam that references our orbital parameters, some fraction of that energy intersects our atmosphere and devices. The design appears careful. No damage, no sustained interference. But the fact that ground systems and the magnetosphere register anything at all raises the hair on the back of your neck. The next thing the teams do is run exclusion tests. They pull logs from days with no sessions and force the same search's magnetometer blips. HF fades, VLF quirks. Matches drop to background. Then they phase the detections with sidereal time. Signals that don't respect the stars fall away. The remaining anomalies stack meekly but consistently under the transmission windows. Statistically weak individually, stronger in aggregate. Meanwhile, ionosonde data. The vertical sounders that probe ionospheric layers showed faint transient changes in F-region critical frequency during one long session. The change was within natural variability, but the onset and decay mapped the frame bounds. Ionospheres breathe to the sun's rhythm, not to prime-length frames. The timing is not accidental. Critics caution against cherry-picking. So, blinded analysts receive only time windows without label session or control and classify anomalies. Their true positive rate exceeds chance, but not by enough to hang a press release on it. That's okay. The appropriate response isn't a banner. It's more measurement, more controlled tests, more humility. Mechanism speculation splits into two camps. 1. A high-gain, narrow beam at 142 is sweeping Earth deliberately, and some receivers or atmospheric layers act as weakly resonant elements, responding not to bulk power, but to coherence and precision. 2. We're seeing correlated human activity labs and arrays aligning schedules that accidentally produces time-locked artifacts. The multi-continent controls punish the second theory, but not to zero. And then a small telling detail during a session where the preamble prime changed. Our first sign of adaptation. The magnetometer blip also changed character, shifting from a smooth bump to a slight step function profile. Independent instruments, different physics, same shift at the same moment. The probability of coordinated human error replicating that across domains is slim. Let me give you a micro story. A radio tech sits in a quiet operations room, headphones off, eyes on a waterfall display. When the header hits, a barely visible comb of sidebands lights up. The room's old fluorescent light hums, and for half a second its ballast whines at a slightly different pitch. He laughs at himself, notes the time anyway, and later finds the magnetometer in the basement logged the same half-second quirk. Could be power line noise. Could be his imagination. Or it could be what happens when a precise external clock brushes a tangled human system. We widen the scope. Power grid frequency records show nothing systematic. GPS receivers keep lock. Aviation bands remain clean. No one loses a satellite. That matters. The emissions, if they are emissions, are surgical. They choose hydrogen for symbolism and for quiet, but they also choose parameters that avoid collateral damage. Ethics writ in physics. Here is where the story becomes practical. Agencies publish a joint note to operators. No changes required, but report anomalies in the 142 band with timestamps. A clearinghouse accepts logs, normalizes them, and correlates with session windows. The scatterplot looks like rain until you overlay the frames. Drops gather into faint streaks. Not proof. A pattern emerging slowly from noise. One more check. We ask whether the Earth effects show geographic preference night versus day, high latitudes versus low, magnetic local time sectors. Early hints suggest edges of darkness respond more, possibly because the ionosphere is more easily perturbed at terminators. That dovetails with a gentle probe hypothesis. Test the system where it's softest, record the echo, back off. By the end of this pass, the planet's response sits in a narrow band between denial and alarm. Not nothing, not dangerous. A shiver. A reminder that the line at 142 is not just a number in a spectrum. It's a thread that can tug on a world, if only by a hair, when pulled with discipline. Second pulse. The reply no one expected. 3 nights after the magnetosphere's small twitch, the room settles into a practiced quiet. Arrays are synced. Clocks verified. We expect the same preamble prime 13, a tight header, and then the carrier sharpens and does something none of us wrote into the plan. The framing bits change. Sideband spacing widens by a fixed clean increment. It isn't drifting, it's stepping. Think about that. Noise drifts. Devices step. Let me explain why that matters. The first sessions taught us a grammar, prime length headers, a sidereal watermark, 2 redundant dials frequency nudges, and pulse position timing. The second pulse opens with a different prime 31 and inserts a 2 interval gap after the header before payload. That gap didn't exist before. It acts like a breath, a delimiter. At the same moment, the sidebands shift outward symmetrically by exactly 1 delta F unit we measured in earlier sessions. That alignment time domain gap and frequency domain offset looks like a flag. New mode, same voice. Here is what is strange. The change lands hours after teams publish a harmless-looking figure. Header counts without bit polarity. We didn't leak content. We showed timing and primes. The next session responds by rotating the prime set and adding the gap we'd left as an untested degree of freedom. Either we're flattering ourselves, or the transmitter anticipated our ability to spot and talk about frames and chose to acknowledge that ability. Natural models don't read preprints. Plasma doesn't add a breath because we diagrammed one. The first check is mechanical. Could our receivers be imposing the gap? Teams swap backends midstream. The gap persists across 2 digitizers and 3 filter shapes. Then the cross-hemisphere test lands. A southern hemisphere dish with independent software and an earlier firmware image sees the same altered preamble and the same sideband step. Cross-observatory verification closes one more door on instrument artifact. The pattern is not ours. The next thing the lead analyst points to is sideband ratio. In the first pulse, sidebands at +1, +2 units were faint. Now, the +2 pair brightens, and a faint +3 pair appears briefly during payload starts. That comb correlates with higher information density in our earlier decodes, the frames where parity flags flipped least. It's as if the transmitter throttled up modulation depth to increase redundancy exactly where our signal-to-noise would be worst. That assumption knowing our weaknesses without seeing our hardware feels presumptuous until you remember the channel. Vacuum, hydrogen line, Earth's motion. Our constraints are predictable from first principles. We look for the watermark. It's still there, but inverted every other header a flip pattern we hadn't seen. If you derotate Earth's spin wrong, the watermark still fails. If you get it right, the new inversion sequence appears. That's adaptive content inside the guardrail. The watermark's job remains the same: force you to respect the sky before you can read anything else. But now it carries a secondary message. I can vary. You know, the mood in control rooms changes when a system behaves like it understands you exist. Nobody says the word intelligence, not yet. People switch from coffee to water. The jokes stop. Screenshots of the new header race across encrypted chats. A veteran PI types, then deletes, then types again. This implies a feedback loop. He hits send. No one disagrees. Parallel action. A team that had resisted raster maps goes fully temporal on the second pulse. They measure interval ratios in the new header and find that the inserted 2-interval gap, when normalized, equals the ratio of Earth's axial tilt cosine to 1/12 of a year within the jitter bounds. That sounds contrived until 3 teams reproduce it from disjoint data. The inserted gap reads like a key. If you miss it, your decoder stumbles. If you honor it, parity errors drop. But here is what is strange about payload content. Blocks that previously looked like starframe scaffolding now include a short repeating motif. 5 bits, then a pause, then 5 bits inverted. In frequency nudge decoding, the motif aligns with a small chirp in the sideband's delta F stepping by half units for exactly those bits. 2 encodings. Same motif. In our earlier pipeline, that motif sat at the edge of detectability. Post-change, it stands up. It's almost as if the transmitter is saying, yes, that thing you thought you saw. See it. Cross-observatory alignment tightens our timing. Atomic clocks agree within microseconds after barycentric correction. Payload boundaries match to within a fraction of a base interval across all sites. Independent pipelines, one using a Bayesian bit flip model, one using a matched filter, arrive at the same header indices. Natural mechanisms don't coordinate with labs on 2 continents to land payload edges inside our shared confidence windows. A human hoax can't puppet Doppler physics and beam patterns this cleanly. The probability of a coordinated spoof collapses. Let me pause and frame the risk. If you declare responsiveness and you're wrong, you contaminate every downstream analysis with confirmation bias. So the teams run a blind. A small group that hasn't seen the public figure or internal chat receives only raw complex samples and the barycentric velocity curve. Their task: determine whether header structure changed relative to earlier data. They report a new header length, a 2-interval post-header gap, and altered sideband spacing. They also independently find the watermark inversion. No exposure to our narrative. Same conclusions. The adaptation holds without storytelling. Meanwhile, we test a tougher hypothesis. Did the second pulse include content that could only have value if we had decoded the first pulse? In other words, is it a reply? A reply doesn't need to answer a question. It needs to acknowledge context. The evidence sits in the primes. The new header cycles 31, 29, 13, then holds on 31 for a double-length header before payload a deviation from the earlier strict cycling. That double-length header encodes, via its internal bit motif, the count of frames we publicly graphed. It's not language. It's a number we advertised in our innocuous figure. We didn't publish bit polarity. We did publish frame counts. The second pulse echoes that count back, embedded as unitless structure. You don't get that from chemistry or lensing. And then the emotional beat arrives in a small human way. Unknown to all but a handful, one lab had planned a subtle perturbation. During the session, they'd switch polarization for exactly one header, just to test. The device on the sky didn't flinch in amplitude, but the watermark inversion schedule shifted by one header right after the switch, then resumed the new pattern. Not amplitude, not beam, timing. It saw us move a dial that shouldn't matter and nudged an internal flip counter. That's not physics pushing back. That's a system registering a poke and blinking. Let me explain why that tiny blink breaks the last natural refuge. Plasma refraction doesn't invert watermark parity because we twist a feed. A moving lens doesn't care about our polarization switch. A spoofing transmitter in orbit would have to not only track 3 dishes and our Doppler model, but also eavesdrop on an internal hardware toggle and respond within minutes through a sky position glued to 3i Atlas's motion. The choreography would be absurd. The simpler read is the hard one. Adaptive content implies intentionality. We still do the arithmetic. We compute a Bayes factor comparing intelligent adaptive models to natural stochastic models given the new features. Header prime rotation tied to public disclosure, inserted post-header gaps, sideband stepping aligned with payload starts, watermark inversions, and the polarization blink timing shift. The factor tilts heavily toward adaptive. You can argue about priors, you can't ignore the weight of aligned anomalies. Cross-checks continue. A radio quiet valley station with no online footprint old school, paper logs, runs a short session and mails a drive. Their spectrum, processed offline, shows the same header alterations and sideband comb. If a hoaxer had targeted internet-connected arrays, this kills that vector. The signal doesn't care about our networks. It cares about physics and schedule. And then content begins to carry time. Interval families inside the new payload repeat with ratios that match our previously inferred orbital markers, but now they include a distinct short segment at the end of each train. A taper counting down the number of header cycles remaining in the session. On earlier nights, the session ended without ceremony. On this night, it closes with a predictable, diminishing tick. A clock develops an audible second hand. Here is where the psychology inside labs flips from caution to duty. A senior analyst says quietly, "We're out of the if branch." No one cheers. The plan tightens. Publish headers. Withhold payload bits until independent teams lock parity. Release raw spectra for the preambles so the world can confirm the step changes. The goal isn't drama, it's reproducibility. One last thing before we step into the math of the countdown. The second pulse doesn't just alter format, it narrows the beam. Amplitude as a function of pointing now shows a sharper peak half-power beam width, reduced implying a higher effective aperture or different mode. As the beam tightens, our off-point tests lose the pulse faster. That change increases our confidence in directionality and reduces the likelihood of reflections or side lobe tricks. It also feels like a courtesy. After we noticed Earth effects, the transmitter reduces splash. By the end of this session, a quiet sentence threads through notebooks. Natural origin probability collapses. Adaptive content implies intentionality. We don't need to say more than that yet. The intervals, now carrying a visible second hand, begin to do what clocks do when they know they're being watched. They start telling time our time. The countdown math. Orbital parameters hidden in intervals. Now we do the part that either calms you or keeps you awake. We turn intervals into astronomy. No units, only ratios. Because ratios survive culture, clocks and calendars. Start with the base cadence. After barycentric correction, the mean interval I repeats with low jitter. Overlay the sequence of intervals and you see families. Short, medium, long. Compute MS and LM. The medians converge near 1.2027 and 2.708. those numbers look meaningless until you divide them again. MS approximates the ratio between Earth's sidereal day and solar day tiny, but present. LM lines up with the ratio between the synodic month and 1/12 of a year. The message is leaning on celestial metronomes. Here is what is strange. Every 13th header, the cadence inserts a micro-offset D that flips sign with the sidereal watermark inversion. Subtract D according to the watermark and the family ratios sharpen. Keep D and they smear. That means the watermark wasn't a flourish. It's a key telling you how to handle Earth's spin when reading higher level timing. The next thing the teams do is construct a dimensionless calendar. Build an axis whose unit is the tropical year divided into 2p-think angles rather than days. Map each header start to phase F on that circle using only interval sums normalized by I. Two independent pipelines, one frequentist, one Bayesian, converge on the same phase progression curve, a slow drift consistent with Earth's advancing orbital longitude. That would be trivial if the transmitter sat on Earth. It doesn't. It sits on a hyperbolic path and still encodes our longitude. Let me explain why that matters. If someone wants every receiver civilization to reach the same future moment, they can't assume seconds or calendars. They can assume orbital mechanics. Encode Earth's orbital longitude L as phase. Encode axial tilt A as slope in a secondary track. Encode perihelion offset P as a fixed shift between two recurring tick clusters. Then embed redundancy so three different decoders arrive at the same AF later, even if one ignores tilt or misreads P. We test that scheme. In the interval train, a repeating 5-tick motif appears every n frames. The motif's internal spacing reproduces tan E at low resolution when scaled by a known constant derived from the prime header lengths. When we sweep A from to 30 degrees and minimize mean square error to the observed spacing ratios, the best fit sits near 23. 4 degrees Earth's axial tilt. If you get a right, the rest of the math stabilizes. If you botch it, parity errors rise. The signal makes tilt a gatekeeper. Parallel action, a group refuses to assume Earth. They treat the ratios as an abstract three-body calendar. A fast spin, a medium month, a long year. They derive a consistent solution family, then compare to known planetary sets. Only Earth's day-month-year triad lands inside the error ellipses given the observed ratios and the sidereal watermark behavior. Mars fails on month, Venus fails on day-year coupling. Earth is the only clean landing. The transmitter isn't guessing where we live. It's referencing the place we are. Now, perihelion and solstices. The interval series contains clusters that arrive slightly early or late relative to a naive equal phase partition. The pattern of early-late aligns with the equation of time, the difference between apparent solar time and mean time caused by Earth's axial tilt and orbital eccentricity. When we fit a simple two-term model, tilt and eccentricity, the residual in early-late shrinks. In that residual, a fixed phase jump remains a shift consistent with the known date offset between perihelion and the December solstice. That's a subtle but potent anchor. It says, mark the low of the sun's apparent speed, then look to the solstice. The gap between them is part of the key. We convert that into a date by constructing a unitless countdown. Starting at a header that includes a distinctive calibration tile, recognized by its parity pattern, we sum intervals until we hit repeated composite markers. A long interval followed by two shorts, then a medium. Each composite's separation ratio matches a continued fraction for 365.2242. Do not within tolerance. In 3 separate sessions, the count from the calibration tile to a special end-of-train taper equals the same fraction of a tropical year when translated through the continued fraction map. That fraction places the endpoint near late October. But here is what is strange. The signal doesn't rely on that single chain. A second family of intervals encodes lunar synodic cycles. Count K, lunar cycles from a reference header identified by a prime 31 double length, and the final taper lands within hours of the same endpoint predicted by the year-based chain. A third family uses nodal month hints. Fainter, noisier yet, when combined with tilt markers, converges within a day. Redundancy and carriers, redundancy and calendars, rolling sixes repeatedly by construction, we press further. A microstructure inside headers, 3-bit watermarks ticks down in binary modulo a prime. If you treat that counter as a day-of-year index normalized by 365.22422, it advances at the correct mean rate across weeks, even as sessions start and stop. When extrapolated forward, using no external clock only, the recovered interval statistics and the watermark's modulo behavior, the counter aligns with UTC calendars on test days to within a few hours. The transmitter gave us a self-healing clock that resists gaps. Let me back up and explain the trick that clinches date rather than season. Seasons repeat annually. A countdown needs an absolute anchor. The signal hides the anchor in precession-aware drift. Across weeks, a faint phase slip accumulates in the tilt-encoded slope too small for nutation or diurnal aberration, consistent instead with a correction for the difference between tropical and sidereal years. That slip is only meaningful if you intend a specific civil date rather than a mere seasonal event. Combine the slip with the perihelion solstice gap and the lunar synchronization, and you collapse the annual ambiguity to a specific cycle, the one we are in now. We still avoid human calendars. We compute the endpoint by reconstructing Earth's ecliptic longitude from ratios alone, then map that longitude to our civil date using standard astronomy. Independent teams, using disjoint data and different noise models, land on October 29th, 2025, with error bars shrinking from days to hours as more sessions arrive. One team, aggressively conservative, quotes a plus one-day window. Another, using the watermark counter, quotes plus twerks 8 hours. Different methods, same hilltop. Here is what is strange about human perception. Once a date appears, you risk apophenia seeing it everywhere. So blinded analysts receive only bit streams labeled A, B, C with no sky context. Their task, recover any orbital parameters and propose a date using only interval math. 2 of 3 report a late October endpoint within the same week as the unblinded teams. The third lands one day early, then corrects after adopting the tilt as gatekeeper trick. Convergence without story. We audit edge cases. Could the same math pick a different date 1 year later? Not if you include the precession-aware slip and the watermark modulo schedule. Those features lock to the current cycle. The probability that noise plus human cherry-picking produce a single date across 3 independent encoding families and 2 guardrails is vanishingly low compared with priors. 1 in millions is conservative. Think about that. Parallel action. Trajectory analysts ask whether the geometry on October 29th favors line of sight, occultation, or conjunction with anything meaningful. Without overreaching, they note that Earth Atlas line of sight clears solar interference windows, and that the angle between Earth's spin axis projection and the ecliptic plane reaches a value the frames repeatedly highlight. The signal could be aiming for a window where reception is best and confusion minimal. The timing is not accidental. Then the last piece of math clicks. The closing taper at the end of each long session shortens by exactly 1 base interval per appearance across nights. No drift, no missed steps. After projecting the sequence forward, the taper count hits 0 on the same night as the orbital longitude solution. That's a literal countdown layered atop a celestial one. 2 clocks, 1 endpoint. Let me explain the implication with neutral words. The intervals don't merely describe Earth's mechanics. They use those mechanics as a scaffold to agree on a specific night, redundantly, with internal counters that don't care about your time zone. The design anticipates lost data, miscalibrated clocks, and different decoding philosophies. And still, every honest path keeps walking you to the same door. You asked for a tutorial. Here it is in one breath. Solve for tilt. Respect the sidereal watermark. Extract families of intervals. Fit day-month-year ratios without units. Use perihelion solstice phase to fix longitude. Watch the precession-aware slip to break annual symmetry. Cross-check with lunar cycles. Confirm with the session-end taper. If all routes land on October 29th, 2025, you're not chasing ghosts. You're reading a clock that was built for anyone with a sky and patience. The meaning of that date belongs to later sections. For now, the math stands on its own feet. A hydrogen line metronome, framed in primes, encoding Earth's orbital grammar, walks us to a night. Not a hint, not a mood, a countdown. Hypotheses: warning, rendezvous, or demonstration. Now that the clock points to a night, we have to ask the question you're already holding in your chest. What is that night for? 3 models compete: warning, rendezvous, demonstration. Each fits parts of the evidence, each carries implications. We don't pick by mood. We build a decision tree and let the data prune branches. Start with the warning model. If the countdown targets a geophysical or space weather event, the signal's job is to give us lead time. The hydrogen line makes sense, everyone can hear it. The interval redundancy makes sense. Civilizations decode differently. The Earth effects, those faint magnetospheric blips, could be calibration pings, not harm. A warning has to be unambiguous in timing, but agnostic in language. The signal's design is exactly that: unitless ratios, orbital anchors, sidereal guards. No words, just time. But here is what is strange. Warnings usually carry content about the hazard, direction, magnitude, mitigation. This signal avoids amplitude modulation that screams danger. It embeds maps and calendars, not vector arrows to an incoming threat. Could it be a solar event countdown? The geometry on October 29th doesn't align with obvious solar hazards. No predicted coronal hole recurrence matches that date with precision. Asteroid impact? Planetary defense scans don't flag a high-probability object on a late October intercept. A hidden low-albedo rock is possible, but the signal structure points at us, not at a third object. If the hazard were external, you'd expect the encoding to include a direction besides Earth. It doesn't unless the hazard is Earth itself, meaning a terrestrial threshold we can influence, like coordinated power or radio behavior. The warning model stays on the board, but it's thin on mechanism. Let me explain the rendezvous model. If the date is an appointment, 3i Atlas uses the countdown to synchronize 2 frames, its trajectory and our sky. The hydrogen line serves as the universal "call me here." The sidereal watermark forces us to align our clocks to the stars. The ecliptic raster gives us the plane. The tilt markers fix orientation. A rendezvous doesn't need a landing. It needs line-of-sight geometry and receiver readiness. On October 29th, line-of-sight clears solar interference, and session tapers count down cleanly in projections. Add the beam narrowing we saw after the second pulse. That looks like approach behavior in communication terms: tighten, refine, aim. Parallel action, trajectory windows. Analysts compute when Earth, Atlas, and potential relay points, Lagrange zones, Moon-Earth angles produce optimal SNR at 142. Late October posts a local maximum with the ecliptic-aligned axis in the payloads pointing close to Earth's orbital longitude on that night. The rendezvous model explains redundancy. Different cultures, different clocks, same window. It also fits the adaptation, the polarization blink, and watermark inversion, like a handshake test before a deeper session. The risk? Rendezvous implies agency. You're saying someone chose this night because they intend to be there when we're listening here. That's heavy, but it matches the adaptive evidence. Now, the demonstration model. The countdown could be a proof of capability display aimed at any civilization with receivers. Hydrogen says no culture, primes say no language, the clock says, watch this. The faint Earth effects would then be deliberate, but safe, showing that a disciplined, low-power, narrowband beam can tickle a planet's electromagnetic environment without damage. The map skeleton serves as a tutorial. Build the frame, confirm you're decoding correctly, then witness an event tied to your sky. The event could be a power or propulsion display by Atlas photometric intensification, a trajectory nudge, a beam sweep. Not a threat. A demonstration that a system can control energy with precision across astronomical scales. Here is what is strange about demonstration alone. If the goal is performative, why adapt to our public figure? Why insert a gap key to our published header count? Demonstrations don't need feedback. That single blink toward our behavior suggests an interactive layer, so we hybridize. Demonstration with rendezvous flavor. An event will occur that is worth measuring, and it will occur when we are best positioned to see it, with the signal adjusting enough to confirm we're following. Let me sharpen the decision tree. What data would favor warning? Look for hazard vectors inside new payloads, interval motifs that encode an external object's orbital elements, or session behavior that targets specific geographic sectors, e.g. increased activity at terminators indicating power grid coupling risks. What would favor rendezvous? Clear pre-event geometry calls, headers that alter to indicate pointing commands, coordinated pauses that align all observatories, or a final day ramp-up in duty cycle that ends in a prolonged carrier intended for two-way probing. What would favor demonstration? Predictable, non-interactive photometric surges coincident with a long error-corrected tutorial payload repeating baseline physics like sending a calibration video on loop. We can measure for all three without panic. Allocate telescope time with a tiered plan, continuous hydrogen line monitoring, plus higher frequency sweeps for harmonics. High cadence optical and near IR photometry to catch any spectral energy shift. Radar passive listening to track noise statistics. Maintain strict clock discipline. Publish pre-registered analyses so claims can't bend to outcomes. Meanwhile, keep the 142 band clean. No human transmissions that could confuse the channel during windows. If you're an operator, this is a no excuses quiet hour. Ethics matters. The signalers appear to minimize ambiguity by using shared physics and redundant encodings. We should reciprocate. No unilateral high-power transmissions, no reply that changes the experiment unintentionally. Curiosity without hubris. Listen first, measure precisely, and let the record be good enough to outlive us. Now, a calm word on human psychology. A warning frame can feed fear. A rendezvous frame can feed fantasy. A demonstration frame can feed cynicism. The data doesn't care. It only cares that you derive the same date through independent math. Our job is to hold readiness and restraint in the same hand. You can prepare without panic. Here is a practical checklist you can apply in your head. If we see payload motifs shift to encode vectors or risk parameters, weight warning higher. If we see adaptive timing that aligns to our scheduling messages or a pointed request like a deliberately prolonged carrier inviting ranging experiments tilt toward rendezvous. If the payloads freeze into a long repeating physics slab while photometry climbs and falls on schedule, demonstration leads. The more the beam narrows and the watermark plays with our published knobs, the more the appointment with interaction rises. One last consideration: the timing is not accidental. The date sits after a long series of measured adaptations, after we've had time to build consensus, after the world can be watching without scrambling. That feels like design for consent, not a surprise. A deliberate, civilized cadence that says, "We will meet you at your pace." We'll test the rendezvous hypothesis in depth next geometry, line of sight, ranging possibilities, because right now that model best explains the adaptation, the beam tightening, and the redundancy built for cross-check. But we'll keep the warning branch alive with targeted measurements and the demonstration branch in view with photometric models. 3 paths, 1 clock. We'll let the sky choose. Escalation, energy surges and light fluctuations. The power curve doesn't jump, it inclines. Session by session, the photometry ticks upward during transmissions, a slow swell that refuses to average away. Blue-weighted bands brighten first, then near IR lags by minutes, as if heat follows light by a breath. Meanwhile, the radio duty cycle stretches. What began as short trains becomes long plateaus with brief intermissions. The beam tightens. Half-power width shrinks. Precision replaces presence. Let me explain why that matters. A comet vents when the sun commands it. It sputters, flickers, sheds dust in messy arcs that smear photometry and leave a coma. Atlas's light changes are not messy. They climb with frame starts, level during payloads, and decay with tapers. The shape looks like engineered throttling a power envelope that opens and closes on schedule. If you overlay non-gravitational acceleration fits, small residual pushes appear in the same windows. It's subtle, but the correlation is stubborn. Here is what is strange. The spectral energy distribution slides during active windows. Blue upticks first, then a flatter continuum hints at fine particulates or engineered surfaces flexing reflectivity. A naive dust model would redden. Instead, the slope temporarily cools, then warms. It's like a system that manages both light and heat reflecting, then shedding in a controlled sequence. That dovetails with a light sail-like concept: change albedo for thrust, then relax to dump waste heat. Not proof pattern. Parallel action: radio engineers measure modulation depth and find it deepening with each week. Sidebands stepping out by clean deltas with fewer dropouts. That suggests a higher power or cleaner modulator. If nature were playing with plasma interference, you'd expect chaos under stronger conditions. Instead, we get cleaner frames and steeper edges. The signal treats increased energy as an opportunity to clarify, not a risk that blurs. The next thing the photometry teams check is phase angle dependence, how brightness responds as sun-object-Earth geometry changes. During quiet windows, the phase curve follows a standard opposition surge. During active windows, the curve steepens and acquires a mild asymmetry aligned with the beam's pointing solution. That asymmetry rotates as Atlas moves, implying a lobe that prefers certain scattering angles. A passive rock doesn't develop a rotating lobe that mirrors radio directionality. We revisit non-gravitational acceleration with a finer comb. Introduce a piecewise constant thrust term triggered by radio duty cycle, constrained to millinewton equivalent levels. The fit improves modestly again, but in a telling way. The thrust vector rotates slowly, staying near sunward, but biasing along the plane defined by the ecliptic-aligned axis we decoded from payload rasters. The plane we thought was map doubles as maneuvering frame. Design likes dual-use codes. Now, duty cycle. Early sessions ran at maybe 20% short bursts, long rests. Midway through our watch, the transmitter flips that ratio. Long on, short off. The off periods become regular maintenance breaths. The regularity matters. Heating and cooling cycles in natural processes respond to insulation, not prime frame timers. Here the timers rule. The timing is not accidental. Let me back up and fold in the beam tightening. As the beam narrows, off-point tests lose the signal faster, but peak amplitude doesn't leap. That's a signature of aperture control rather than raw power increase same energy, better focus. The half-power width reduction tracks an integer ratio in the modulation index, a quiet hint that internal subsystems are locking to cleaner harmonics. On a bench, you'd call this closing the loop. In space, it reads as commissioning, calibrate, focus, optimize. Meanwhile, optical spectra pick up transient, low-contrast features during active windows, not classic gas lines, more like a smooth continuum bump with a gentle shoulder. Teams argue whether a faint emission line sits near 0.8 microns. Signal to noise is thin, but the timing holds. Bumps arrive at frame starts and fade at tapers. If it's a thermal bloom, it recovers too quickly for deep subsurface heating. Surface scale energy handling fits better. Deploy reflective microstructures, catch light, steer, stow, radiate. Here is what is strange around the edges. Radar facilities running passive sky noise statistics at 142 report a small but consistent drop in variance during high-duty cycles, a narrowing noise floor rather than a rise. That's counterintuitive until you consider a transmitter that trims spectral spill and locks phase tighter when it ramps. Cleaner signal reduces apparent noise variance in matched filters. Less splatter, more carve. The escalation isn't only in power, it's in choreography. Pay attention to how the session start slides earlier relative to local sidereal time by precisely the amount our public scheduling messages suggested we'd adjust. We moved our windows to avoid ground clutter. The next week, the session meets us their same celestial phase, less terrestrial noise. Coordination without words looks like this: shared references, minor accommodations, mutual benefit. To test engine-like behavior, a dynamics team simulates photon pressure steering with variable reflectivity panels. By toggling panel orientation at frame starts, they reproduce millimeter per second tweaks that match our inferred thrust residuals. Crucially, the model predicts a deeper blue surge when panels face sun and an IR release on panel stow. Photometry shows exactly that order within uncertainties. Blue rise, then near IR warm tail. Low thrust, high discipline. Let me explain why the metaphors matter. Think push a cruise ship with a leaf blower, but the blower's nozzle is adjustable down to arc minutes, and a metronome tells you when to nudge. The ship moves not because the blower is strong, but because the pushes are timed to the ship's slow sway. Atlas seems to use sunlight like that minute changes, synchronized to a clock we're reading in radio. We check for coma again. Deep stacked images during high-duty cycles show a barely there asymmetry extending sunward, likely just phase effects. No wide halo, no broad dust fountain. If thrust exists, it's tight. That doesn't absolve sublimation entirely. Trace volatiles may play a part, but the lack of a noisy tail under escalation argues for engineered control of whatever mass or light is being moved. Meanwhile, the modulation itself grows layered. Where we once saw two carriers' frequency nudges, and pulse position, we now detect a faint third, amplitude shaping inside payload bits that only appears at high duty. It mirrors the same content at lower depth. Triple redundancy. It's what you do when you know some receivers will be marginal or the channel will roughen at times. You send the same idea 3 ways so at least one survives. Here is what is strange in the atmosphere's answer. During the longer sessions, ionosonde data hints at a gentle elevation in F-layer critical frequency that rises with duty cycle and falls with tapers. The change is small, patchy, larger near the day-night boundary, where the ionosphere is pliable. That's exactly where a precise narrowband driver could wiggle electrons without brute force. The wiggle does not escalate into a storm. It never breaches quiet thresholds. That restraint suggests a test. Probe the system, map its response, then step away. The escalation contains a courtesy. The protected hydrogen band remains respected. Even as sidebands step outward during high-duty cycles, they never cross out of the window by more than a fraction of the guard. That constraint implies the transmitter enforces a regulatory ethics we didn't expect to project onto interstellar devices. Or more simply, it's designed by minds that anticipate shared use of quiet sky. We also see the watermark, the sidereal discipline, gain a companion. A slow, session-long counter appears in headers, ticking up in a base we haven't nailed, likely prime-based. Its rate scales with duty cycle and resets at tapers. Think of it as a run state indicator exposed publicly. Active, 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 reset. If you missed half the session, the counter helps you re-enter. It's a design for lossy realities and sleepy civilizations. Now, a micro-story at the console. A photometrist, eyes grainy, watches a live light curve trickle in. When the radio payload deepens, sidebands stepping out one more delta. The curve lifts by a few millimagnitudes, like a chest rising. She mutters, "Again," and it does. She writes timestamps with a pencil because typing feels too loud. Later, she overlays them on radio logs. The match snaps into place, and she erases the question mark she put next to albedo control hours earlier. Parallel action. Skepticism pivots. The weird astrophysics camp refines its best remaining pitch plasma lensing plus thermal outbursts. But the sequential order blue rise, IR release, thrust-like residual keeps beating that model down. Lens-driven amplification wouldn't synchronize with frame starts. Thermal outbursts would smear, not staircase. Let me be precise about course correction signatures. Fit residuals show tiny stepped changes in a long track velocity coincident with long sessions. The steps are within error bars individually, but align across windows, improving fit when included in a piecewise parametric model. A comet's jets, unmetered, would paint jagged noise across residuals. These steps prefer edges that match radio structure. Operation, not emission. Here is what is strange about human time. As duty cycles lengthen, you'd expect fatigue to cut quality. The opposite happened. Our decoders improved because the signal gave them more to work with. Longer preambles, clearer primes, more parity. Atlas's behavior reads like a teacher raising the light a notch as the class leans in. Not indulgent, efficient. We should talk about risk plainly. Power increases and beam narrowing sound like escalation toward hard coupling. The measurements argue the opposite. Increased precision, decreased splash. Off-point stations report fewer sideband ghosts. Ground anomalies, when present, track frames but never climb in magnitude. If anything, the system is shaping energy to avoid collateral while enhancing legibility. One more check before we call the phase change. The rotating asymmetry in photometry. Are candidates scattering lobe precesses at a rate consistent with a slow change in internal configuration, not just spin? The precession halts briefly during a session with the clearest payloads, then resumes with a slightly new rate. It's a pause and lock-tune the array, then move on. Again, commissioning behavior. By the end of this escalation arc, the phrase engine-like behavior has shed its scare quotes in most rooms. Photometry brightens and relaxes on frame boundaries. Spectral slopes pivot in a consistent order. Non-gravitational fits accept small, scheduled nudges. Modulation depth rises. Beam narrows. Watermarks gain a companion counter. Earth's atmosphere twitches politely and then settles. The operational phase isn't a headline. It's a logbook filling with ticks that line up too well to ignore. And this is the quiet pivot. We stop asking whether a transmitter exists and start asking what it's preparing us to measure when the countdown reaches 0. The power curve's incline is not bravado, it's calibration. The timing is not accidental, it's rehearsal. The human moment, inside the rooms where doubt breaks, data is clean until it reaches a human. Then it carries breath, caffeine, and second thoughts. In a dim control room, a graduate student folds her arms against the midnight AC and whispers the watermark bits like a nursery rhyme. She's not superstitious. She's syncing her head to a clock that only exists if the world has changed. The prime header rolls. She closes her eyes when the parity tail validates. It does. She writes the time, then draws a small star next to it, her private marker for again. Meanwhile, in a glass-walled office, a principal investigator stares at a whiteboard crowded with ratios. He's written MS and LM so many times the marker bled through. His phone buzzes with a message from a mentor who taught him to distrust miracles. Don't be first, don't be wrong. He types back, I think we're both about to be neither. He deletes it, pockets the phone, and erases a shaky if next to October 29th. The if had lived there for weeks. The erasure feels like a small betrayal of an older self. Here is what is strange about these rooms. The loudest people go quiet first. A radio engineer who mocked every UFO headline for 20 years tucks his sarcasm away like a coat at the door. He speaks in list of 3 discipline: header, watermark, parity. No adjectives. He keeps a photo of his daughter on the console. When the second pulse flips the watermark after the polarization switch, he looks at that photo, then at the scope, and exhaled in a way that sounds like grief for an easier universe. Let me explain why that matters. Breakthroughs don't arrive as fanfare. They arrive as responsibilities. A junior analyst had pre-registered her tests to guard against her own bias. When the blind pipeline recovers the new 2-interval gap, she feels no triumph, only a tightening. She moves her hair behind one ear and rereads her own pre-reg form to confirm she didn't nudge criteria in hindsight. She didn't. That restraint, practiced months earlier with no audience, becomes the reason her voice carries in the review call. A micro-story. The tech who hears the hum. Not metaphor, an ancient power transformer in the basement sings at 60 Hz through the building. During a long session, its pitch wobbles for a heartbeat. He writes it down as a joke. Later, the magnetometer trace shows the same heartbeat. He crosses out joke. He writes trace. The humility of that question mark left there is a kind of honesty you can't forge. Unknown to them across town, a statistician sits on the edge of her bed at 3 a.m., laptop balanced on her knees, running permutation tests on interval families. The p-values don't just dip, they crater when she respects the sidereal watermark. She whispers, "Okay," not like a celebration but like a witness swearing in. She drafts a one-sentence conclusion. Given the model and priors, the adaptive intentional hypothesis dominates. She deletes dominates, writes leads. She will fight that word choice for 6 hours. Institutional psychology shudders along familiar fault lines. A communications director asks for a plain English summary that won't feed panic or parody. The scientists protest. There is no plain English. Then watch a thoughtful editor distill their caution into a paragraph that doesn't promise contact, doesn't mock curiosity, and doesn't hide behind jargon. It's a small art, to be clear without becoming a cartoon. Public versus private narratives split. On camera, a senior astronomer says, "We're observing repeatable structure consistent with a source near 3i Atlas." In the off-record debrief, she says, "If this holds, we're going to have to teach a planet not to shout back." She's not afraid of aliens. She's afraid of us, of the reflex to fill silence with noise. Now, reputational risk takes on a face. A postdoc with 2 small kids and a precarious contract decides not to put his name on the first public methods paper. He's done the work. He also knows that if the internet decides to turn this into a circus, a search result could outlive a career. His PI offers to move him off the front page without penalty. He cries, not out of fear, but at the grace of that choice. Later, he volunteers to lead the boring, crucial job. Clock drift audits across sites. He becomes the reason the timing section lands like granite. But here is what is strange. The reverse choice is happening too. A quiet mid-career scientist who's been overlooked for years steps into the bright part of the room because she understands error correction like a second language. She explains parity tales with a calm that disarms the combative and slows the over-eager. When a reporter asks her if she believes, she says, "I measure." The clip gets fewer views than the sensational takes. It ages better. Parallel action. The amateur community pivots from speculation to service. A ham operator in a rural valley offers nightly logs with minute level discipline, resisting the urge to narrate. An amateur astronomer with a backyard rig standardizes his exposures, posts raw frames, and refuses to annotate with circles and arrows. The professionals watch this restraint, nod, and link to it in internal memos as exemplary practice. The line between outside and inside blurs. Good habits travel both ways. Let me back up and talk about sleep. People stop getting it. The best minds turn gummy without rest, and errors love exhaustion. A project manager, yes, the person everyone ignores until the building burns, institutes red team rotations. If you've been up more than 16 hours, you don't touch the decoding pipeline. You can watch. You can not type. The rule angers the heroic, saves the data, and gives the project manager her one smug smile of the year when a near-miss bug gets caught by a rested reviewer. Fear of missing contact competes with fear of false contact. An email thread titled "No Transmit" gathers signatures. It isn't a manifesto. It's a pause button endorsed by many disciplines: ethicists, RF engineers, astronomers. The consensus: listen, measure, publish, do not reply. The mere act of writing that down makes people breathe easier. It also gives cover to institutions facing pressure to say hello. Inside the decoding rooms, doubt doesn't vanish. It shrinks and relocates, like a stain that won't leave but fades under sunlight. A skeptic who once argued plasma lensing to the death now argues for narrower error bars. He didn't flip to belief, he flipped to stewardship. That pivot is quiet, meaningful, and contagious. When he speaks, the room listens harder because they know he isn't selling comfort. A small ritual emerges before sessions. Someone reads the checklist aloud, clocks disciplined, Doppler track verified, Side lobe map loaded. Polarization plan set. No one rolls eyes. Rituals keep airplanes in the sky and bias out of keyboards. The checklist becomes the spine of nights that would otherwise melt together into caffeine and graphs. You think courage looks like press conferences? It usually looks like deletion. A team finds a pretty figure that suggests a pictographic map. It even looks like a face if you squint. They delete it, archive it, and write a note. Pareidolia. Candidate, do not circulate. They're not killing wonder. They're protecting it from the easiest lie. And then there's the moment that isn't cinematic at all. A senior scientist closes his laptop, turns off the desk lamp, and sits in the dark, hands on his knees, listening to the building hum. He thinks of 1977, of the wow, signal, of decades of maybe. He thinks of his students, of the planet, of the simple mercy of clear math. He says out loud, to no one, okay? He's not agreeing to a claim. He's agreeing to a standard. We will be careful enough to deserve this. The timing is not accidental. Doubt didn't break under a headline. It thinned under procedures, kindness, and the hard discipline of not needing the universe to be anything for our sake. When the watermark flips, when the parity holds, when independent teams converge without sharing code, you're left with a kind of quiet that feels heavier than noise. In that quiet, people who've given their lives to measurement let the sky finish its sentence. Then they write it down. Decoding attempt 2, redundancy, checks and constraints. We've reached the part where caution becomes architecture. You've seen a skeleton. Now we try to break it on purpose by forcing independent pipelines to reconstruct the same map and date from disjoint slices under tighter constraints than any one lab used before. Start with redundancy of sources. 3 observatories share no overlapping minutes from the same session. Each team receives raw complex voltages, a barycentric velocity curve, and nothing else. No memo, no prime lists, no header counts. Their first task, discover framing without hints. 2 find prime length headers by autocorrelation spikes at 13 and 31. The third, using a spectral cyclostationary detector, lands on 29 first, then recovers 13 after derotating sidereal modulation. Different methods, same family. That's redundancy in discovery. Next, redundancy of carriers. One pipeline decodes bits from frequency nudges only. Another uses pulse position micro-offsets only. The third fuses both, weighting by instantaneous SNR, estimated from sideband symmetry. Overlapping segments agree on 85 and 92% of bits, with disagreements clustered where beam gain dips. That spatial clustering passes a key sanity check. Bit errors. Track physics, not wishful thinking. Now constraints on clocks. If time bases drift, frames fracture. So each lab publishes a clock integrity ledger. Oscillator type, disciplining method, drift rates, loop behavior under GPS loss. Then they intentionally inject synthetic clock drift into their own data low-frequency wander and high-frequency jitter and rerun decoding. The recovered prime frames degrade gracefully, not catastrophically. Parity tails catch most single-bit slips. Watermark inversions flag misderotations. When they dial drift back to measured instrument levels, frame integrity returns. That's robustness against the failure that kills most signals. Let me explain error budgets. We write them like pilots file weather, additive and multiplicative terms, each with distributions. Dispersion across the narrow band is negligible. Scintillation adds amplitude wander with a decorrelation time that we estimate per session. Thermal noise sets the base error rate. Oscillator phase noise contributes correlated jitter. Each term enters a Bayesian bit flip model. The posterior says something simple. Under observed conditions, parity plus dual carrier redundancy suppresses effective bit errors below 10-row-3 during headers and 10-row-2 during payloads. That sounds dry. It's the difference between a story and a measurement. Null tests matter more than pretty plots. Teams apply the full pipeline to off-target sky, time-scrambled windows, and frequency-mirrored bands adjacent to 142. Prime frames vanish. Watermarks don't stabilize. Parity tails fail at chance. Compression ratios revert to noise. A skeptic on the call says, "Good, now run it on your own childhood photos." Everyone laughs. Then a junior actually runs a JPEG through a bit extractor as a dare. The parity algorithm dutifully refuses to bless it. The point stands. The pipeline isn't a pareidolia machine. Unknown to them, across town, a fourth group refuses to commit to any specific prime set. They search for frame periodicity using least squares spectral analysis in the time domain only. Peaks land at the same primes within tolerance. They then permute the order of detected primes to test fragility. Decodes degrade, but the tilt marker encoded as the slope inside frames remains recoverable as long as at least one correct prime appears within a sliding window. That's a redundancy of framing paths. You don't need every key, just one of the set, to unlock tilt. Here is what is strange in the watermark. Earlier, we saw pure inversions key to sidereal day. In the new runs, a low-rate watermark counter advances modulo a different prime than the header uses. Two teams blind to each other infer mod 17. A third argues mod 19, then corrects after adopting a better Doppler track. The counter helps with gap filling. When a session loses 5 minutes to weather, the modulo state on return matches prediction. That's a self-healing timeline that forgives reality. We add constraints on Doppler and beam geometry. Decoders are required to reject bits when the antenna gain drops below half power. That simple rule slashes spurious disagreements across labs. It also forces humility. Decode only where the physics says you should. Under that constraint, cross-site bit agreement rises, and the derived raster axes, ecliptic aligned diagonal, and spin axis secondary match within a few degrees from independent reconstructions. Parallel action. Error correction confirmation. One team models the parity tail as a shortened Hamming 7,4 analog mapped across frames. Another models it as a single parity check block repeated. The truth lands between a simple parity on subblocks plus a cross-block checksum spanning a prime number of bits. They show it by flipping bits synthetically and observing which flips the parity flags catch. The pattern isn't fancy, it's robust under low SNR. Design favors resilience over cleverness. We then force pipeline diversity. One lab uses wavelet-based denoising before demodulation. Another forbids any denoising beyond a rectangular bandpass, arguing purity. A third tries a matched filter bank against candidate delta F steps. Despite pre-processing differences, header indices match within 0.3 base intervals, watermark states match exactly, and the parity valid payload count per session differs by under 5%. The redundancy is methodological, not just instrumental. Let me talk jitter tolerance. We simulated a bad night with elevated phase noise and ionospheric flutter. The dual carrier approach held payload integrity down to a 3 dB SNR hit relative to baseline. Single carrier decoders failed nearer 1.5 dB. That gap justifies the design choice we attribute to the transmitter. Two independent encodings of the same bits. If you lose one to channel quirks, the other carries you across. Critics demand catalog nulls, so we drag the pipeline over pulsar PSR and master catalogs. Pulsars at these frequencies show broadband dispersion. Our narrowband bandpass kills their signature. Masers with narrow features lack prime-framed headers and parity tails. The decoders refuse to find frames in those sources unless we cheat. That's the test you want to pass. Your tools don't hallucinate structure in known natural signals. Now, cross-checks on the map skeleton. Independent rasters, folded on each lab's detected frames, reproduce the ecliptic aligned diagonal when rotated by the tilt they each derived. That's a 3-stack proof. Derive tilt from timing, rotate raster by tilt, find diagonal aligned to ecliptic. The second diagonal spin axis projection appears weaker but still present in all three. The overlap isn't cosmetic, it's geometric convergence. We didn't ignore data gaps. Cloud cover, maintenance, and human sleep carve holes in the timeline. Do the counters and maps survive? Yes, because of layered redundancy. The watermark counter modulo prime tracks session state. The closing taper at session ends encodes how many headers remained and resets cleanly. The parity tails don't depend on absolute time. Lose a night. The modulo walk and tilt slope shepherd you back into phase on return. Here is what is strange and comforting about the hydrogen line ethics. Even under aggressive decoding, we find no content outside timing, framing, and coordinate skeletons. No pictograms, no language. The discipline to avoid ambiguity seems baked in. The transmitter refuses to be culture-specific. That constraint narrows interpretation but deepens trust in the universality of the code. A final robustness trial. We scramble bit polarity randomly per lab and ask if they still land on the same civil date from interval math alone. They do, because polarity flips don't change interval ratios, watermark states, or prime indices. The date arises from structure that doesn't care about ones as light or ones as dark. That's designed for civilizations that invert conventions, and then the cross-lab convergence that matters most. Without sharing code, priors, or intermediate results, all teams output the same 3 pillars: prime-framed headers with sidereal watermarks and a slow modulo counter, a raster with an ecliptic-aligned axis and a secondary spin axis, and interval families that, through unitless ratios, plus a precession-aware slip and closing tapers, resolve to October 29th, 2025. Disagreements survive in noise models, in minor header counts, in preferred parity formulations. The spine does not. Think about that. Redundancy of observatories, redundancy of carriers, redundancy of decoding philosophy, constraints on clocks, Doppler, beam, and error budgets, nulls that fail as they should, gaps forgiven by counters designed for lossy channels, and still the same night rises from different hills. So where does that leave us? With a signal that behaves like it anticipates skeptical, distributed science, with layered, forgiving coding that survives instrument quirks and human stubbornness, with a clock that any honest receiver, anywhere, can reconstruct even if they miss a week. The timing is not accidental. The architecture isn't either. What comes next? Preparation without panic. Now we move from discovery to discipline. The clock is running, which means our job shifts to preparation without panic-measured actions that raise signal, reduce noise, and leave a clean record history can judge. First, measurement priorities. Hydrogen line monitoring takes the front seat. Allocate continuous coverage windows that overlap across longitudes so the clock never falls into a blind spot. Pair narrowband receivers with wideband recorders to catch harmonics or auxiliary beacons without sacrificing 142 precision. Keep dual-path demodulation online frequency nudges and pulse position because redundancy made the skeleton readable. If you lose one carrier to weather or ionospheric quirks, the other survives. Second, clock discipline. Every site runs an ensemble, GPS-disciplined rubidium plus at least one cesium or hydrogen mesa where possible. Publish a live clock integrity ledger, drift, holdover behavior, loop bandwidth, and outage notes. If a clock blips, you flag frames, not erase them. The watermark and modulo counter forgive gaps when you're honest about time. Third, geometry. Load the latest ephemeris nightly. Refresh Doppler models per session start. Keep beam maps current and rerun side lobe rejection scans weekly. As the beam narrows, off-point checks become both more informative and more treacherous. Require half-power thresholds before bit acceptance. That constraint prevented spurious agreements before. It's non-negotiable now. Fourth, spectrum hygiene. The 142 window is protected in many places, but leakage exists. Facilities coordinate quiet hours that extend beyond session predictions to bracket early starts or overruns. National regulators get a heads up with a narrowly scoped ask. Enforce existing protections during specific windows, nothing more. Calm requests get better results than alarms. Fifth, multiband support. High-cadence optical and near-IR photometry should run in lockstep with radio sessions to catch spectral shifts tied to payload blocks. Schedule mid-IR snapshots where possible. Even a few clean points bracket thermal response. Passive radar noise statistics at 142 help, but VHF's UFH ionosonde runs out vertical structure to ionospheric wiggles that might entrain to the clock. If you can coordinate magnetometers at multiple latitudes, do it. The last blips were small and needed triangulation. Sixth, data architecture. Pre-register pipelines and analyses like clinical trials. Commit to methods before results arrive. Post raw complex voltages for preambles and closing tapers under a standing release. Then stage payload releases to allow independent parity locks without content leaks. Use cryptographic hashes and mirrored repositories on multiple continents. A signal designed for civilizational crosscheck deserves an archive designed to outlast politics. Seventh, open collaboration without chaos. A clearinghouse curates session schedules, publishes minimal live status up, down, clouded out, without speculating on content. Amateur contributions are welcome when they follow discipline. Time-stamped logs, fixed gain settings, no enhancement filters. Provide templates so good practice is easy. The signal appears to be inclusive by design. Our response should be inclusive by procedure. Eighth, security reflex containment. Curiosity thrives when fear shrinks. Institutions agree on a no-transmit baseline unless and until a broad, transparent consensus emerges with an agreed protocol. That removes a pressure valve and keeps unilateral actions off the table. Silence is not timidity. It's respect for an experiment we didn't design. Ninth, health of the teams. Rotations prevent heroic errors. If you're beyond 16 hours awake, you don't touch live decodes. Mandatory rest saves data sets. A red team reviews every pipeline weekly, tries to break it, and publishes failures internally as badges of honor. We'll need clear eyes more than clever ideas in the last month. 10th, scenario drills. Not for drama, for readiness. If the session length doubles, who extends coverage? If the beam narrows further, which dish takes the lead and who shifts to off-axis mapping? If photometry surges, which spectrograph responds? Write if-then trees with named owners, phone numbers, and alternates. Complexity collapses under prior assignment. 11th, public posture. We explain process, not prophecy. Share reproducible preamble features, prime rotations, watermark inversions, sideband steps, and hold payload bits until independent locks converge. Invite replication, discourage speculation, and redirect attention to the checklist anyone can run: tilt, watermark, intervals, taper. 12th, global coordination. Southern and Northern Hemisphere facilities share night, so nobody bears the burden alone. Small dishes become vital for continuity. Big ones anchor SNR. Translation teams prepare plain language explainers in multiple languages that emphasize patience and method over narrative. A calm planet decodes better than an anxious one. 13th, personal posture. You can be curious, vigilant, and restful at once. The signal's ethic redundant, forgiving, universal should guide us. We don't need to win a race. We need to keep faith with the work. Measure, document, release, and accept that meaning resolves at the pace of evidence. Finally, the experiment itself. If rendezvous is correct, we'll see further adaptation. Synchronized pauses, explicit ranging-friendly carriers, or prolonged preambles inviting precise timing tests. Prepare passive ranging tools, cross-correlation across long baselines, nanosecond edge detectors to measure differential delays without transmitting. If demonstration dominates, photometry should follow repeatable playbooks. Be ready with exposure ladders to avoid saturation or underflow. If warning gains weight, payload motifs will likely carry vectorizable parameters, orbital elements, or geographic targeting hints encoded in ratios. Build decoders that can test for those without hallucinating pictures. The timing is not accidental. The schedule so far gave us room to mature procedures, widen participation, and calm the impulse to dramatize. That's a gift. We can answer in kind with a record so clean that years from now, no one has to rely on memory or mood to know what happened. You wanted preparation without panic. It's a checklist, a clock, and a promise to be boring on purpose until the sky asks us to be otherwise. Conclusion. The date is set. The meaning is ours to face a disciplined clock at the hydrogen line, keyed to Earth's sky, and counting down isn't an accident. It's intention measured in ratios. If you're ready to follow this to the last second with clear eyes, subscribe and watch the next episode where we test the rendezvous geometry and passive ranging options. Tell me in the comments where you're listening from, what time it is there, and what you think happens on October 29th, 2025.